Okay, in this video, all we're going to do is two fractal examples. The first one is called the stair-step fractal. You'll see why. Where I've drawn stage 1 and stage 2, and we need to draw stage 2 and stage 3. And note that segments in stage 0 and respectively 1 have length 1 and 1/2. So the first one, stage 0, that's a 1 and that's a 1. And then stage 1, this one, they're now half the size, but there are twice as many. So we've got 1/2, 1/2, 1/2, 1/2. Okay, on stage 2, notice I kind of penciled in what stage 1 looks like just to make it easier to draw stage 2. Well, this step right here is going to turn into 2 steps. It's going to look like this. Go halfway, and you go up like that. So this is not part of it there, the penciled part. And then likewise, we're going to go halfway to there, up to the right, and up. So none of these penciled areas should exist in stage 2 anymore. So if you think of this as being one step right here, this became 1, 2 steps, and then we got 1, 2, 3, 4 steps. And then what would stage 3 look like? It's going to be 8 steps. So I'm just going to do this, just approximate it. One, 2, 3, 4, 5, 6, 7, 8. That's not very good, but 1, 2, 3, 4, 5, 6, 7, 8. Yeah. All right, well, let's compute the segment lengths in each of them. If this is 1/2, these became 1/4 each. I won't write them all out. And then every one of these became 1/8. There, 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 all of that. So what is the total length? Well, maybe I'll write it underneath stage. I'll write length is 2. It's 1 plus 1. The next length in stage 1, 1, 2, 3, 4. 4 times 1/2 gives us what? 2. No difference. And then what do we have here? 1, 2, 3, 4, 5, 6, 7, 8 times 1/4. 8/4, that's also 2. So it looks like we're getting a constant. In this case, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16. We would have 16 times 1/8 equals 2. So that's pretty interesting. So stage 4, stage 5, every stage is going to have length 2. So the limiting path, that means as stage n goes to infinity, well, it's just going to be 2. So yeah, it's going to be 2. In calculus, if you remember, you have a constant sequence 2, 2, 2, 2, 2, dot, dot, dot. It converges to, you guessed it, the number 2. So the limiting path has length 2. All right, this one's going to be a little tougher to draw. Let's see our second and final example here. Maybe I'll go up a little bit. A little bit more. All right, well, we have stage 0 here and stage 1 drawn here. And rather than drawing stage 2 separately, I'm just going to build on to stage 1 to get stage 2, and then I'll build onto that to get stage 3. But we'll compute their areas in the meantime. Okay. Stages 0 and 1 have areas 1 and 2 respectively. Okay, so now we can kind of see what's going on. Oh, I already have it written down here. Area is 1. So this is a unit square. Well, what did we do? This is stage 0. Here's stage 1. Maybe I'll write it here. Area equals 1. And this stage 0, stage 1, what did we do? We took that square, and on each of the corners, we put another square. How big are these squares? Well, if you took all 4 of them, they would make up this square. So the 4 of these add up together to give me area 2, correct? So it's the area 1 plus, oh, here it is. This one came from that one. This is the big square in the middle. And then we have 4 squares, each one having area 1/4, correct? So 1/4 of this square. So stage 1 gives us an area of 2. We went from 1 to 2. Well, now we're going to proceed with a common pattern. With these 4 squares on the outside, we're going to produce 3 more squares like this. Each one of these squares is 1/4 the size of the big square it's touching, the bigger square. Notice I'm not getting 4 of them, I'm just getting 3 of them on each one of these. Well, I hate to mark over that, but I will. Certainly isn't perfect. But you get the idea. These 3 squares I added here would make up 3/4 of this. So it's like having 3 of those squares added onto it. I made them a little bit too big, I think, but you get the idea. Let me go ahead and finish this up. Okay, so now for stage 2, it's all of the shaded area plus it's all of these as well. All of those. So the stage 2 area is going to start off the same. It's 1 plus 4 times 1/4 plus. Okay, what's the area of all of these small squares? Well, notice that for each one of these 4 squares, I added 3 little ones, and those 3 little ones, area adds up to 3/4 of this square. These 3 are area 3/4 of this square. These 3 add up to 3/4 of this square. These 3 add up to 3/4 of this square. So stage 2 increases by 3/4 of the amount that stage 1 increased by. That's what stage 1 increased by. It started with the 1 and it added this. This is the increase. So I need to add 3/4 of this one more time. So 4 times 1/4 times 3/4. Oops. Okay, so this is the same as this, and then this is the amount that I just added for stage 2. It's all of these little squares on the outside. I'm going to try one more, and I'm going to draw all of them. It would take too long. I'll let you do that. But the next stage, maybe I'll use a different colored pen here. On each one of these outer squares, we're going to do the same thing. We're going to go out half of the size, like this. Okay, that's enough. You'd want to do it all the way around. And actually, go ahead and do that. Let's see, my guess is those would actually be touching, but that doesn't matter. Okay, so now how much have we added? Well, we started off with the same amount as in the previous stage. And how much did we add? Well, this amount right here was these blue squares added. And how much more did we add with these little squares? With each one of those blue squares, like this one, I added 3/4 of that. So I added 3/4 for every single one of those. So stage 3 increases by 3/4 of the amount that stage 2 increased by. So I need to add 3/4 more of this. So I'm going to say plus 4 times 1/4 times 3/4 squared. And you can start seeing what the pattern would look like. Maybe I'll skip stage 4. Maybe I'll go straight to stage 5. The area is going to be 1 plus 4 times 1/4 plus 4 times 1/4 times 3/4 plus 4 times 1/4 times 3/4 squared. Now I need 2 more terms, so plus 4 times 1/4 times 3/4 to the third plus 4 times 1/4 times 3/4 to the third. To the fourth. And if you'll notice, I didn't simplify yet. All of this is going to simplify greatly. Stage 5 area is 1 plus 1, right? That's 4 times a fourth is equal to 1. So that's going to be a 1, that's going to be a 1. All of them have that 4 times 1/4, which is just 1. So that's going to be plus 3/4 plus 3/4 squared plus 3/4 to the third plus 3/4 to the fourth. And now we have the pattern. The limiting area is, in other words, as n goes to infinity, as we go towards stage infinity, it's going to be this just continued on forever. 1 plus 1 plus 3/4 plus 3/4 squared plus 3/4 to the third. I'm just going to put plus dot dot dot. I'm sorry, that's a little messy. So we almost have a geometric series. The only reason we don't is because we have that extra 1 in the front. So this is going to be equal to 1 plus, and here's the geometric series. It starts with this 1. And it starts with 1. And then what is the common ratio? It's 3/4. So this one just corresponds with this one. This part, the geometric series, is going to converge to 1 over 1 minus r, which is 3/4. Let's simplify that. That's going to be 1 plus 1 over 1 minus 3/4 is 1/4. Well, that's equal to 1 plus 4, or 5. 5. So that shows us that the limiting area of this, as we go on infinitely, keep increasing it with tiny squares, tiny squares, tiny squares going outward, the limiting area is going to be 5.